without further ado, let's welcome Vincenzo.
Thank you. All right. Okay. Thank you. Can you hear me? First of all, is everything fine? Yeah. So thank you for the introduction. Thank you all for being here and rather than being on the trails. So today, as Farid said, I hope to give you an idea of how neutrinos open new vistas on this new world of physics beyond the standard model. So, as we all know, the standard model encodes our knowledge of the known building block of nature and their interactions, but is at best incomplete. Because first of all, it does not encompass gravity, and then there's a bunch of other theoretical shortcomings which I won't go into. Most importantly, from a pragmatic perspective, it has a number of phenomenological shortcomings. I like to say, if you were to do a simulation of the universe, starting with the standard model of particle physics and standard model of cosmology, you don't get back the universe as we observe it. So I try to summarize here what I think are the major shortcomings in the standard models. There's no neutrino mass. The neutrino, these elusive particles that we talk about, have mass, and there's no mass in the standard model. There's no matter. So the evolution would give you a universe field of radiation, not baryons. So all the stuff we're made of would not come out of this evolution. There's no dark matter, or for which we have ample evidence. No, and there's no dark energy, this mysterious thing that causes the universe accelerated expansion. So one way or the other, one needs new physics, either in the cosmological model, either in the fundamental interaction, or in both, most likely. And it turns out neutrinos are at the forefront of the searches for new physics because, for one, we need to try to understand the mysteries related to neutrino, like their mass, the origin and nature of neutrino mass. But also, by doing so, you can shed light on other mysteries, like the mystery of how the baryon asymmetry was generated during cosmic evolution. What could be dark matter? What would be dark energy? This sounds like a funny statement, but the literature is full of, so these connections are real. Models of neutrino mass often come with an extra bonus that can give you the baryon asymmetry. This is the strongest connection. There is connection with models of dark matter. Neutrinos could be a component of dark matter. And there's even connection with the dark sector and dark energy. So neutrinos are really central. There are many connections, but today I will focus on one of these hadronic or nuclear probes. So this process of so-called neutrino-less double beta decay, which is a process in which two neutrons inside the nucleus turns into two protons with emission of two electrons and no neutrinos. This plays a special role in neutrino physics because observation would pretty dramatically point to the mechanism of neutrino mass generation, but also tell us that neutrinos are Majorana particles, so their own antiparticles. And as a bonus, we would establish one of the key elements for a class of baryogenesis mechanisms called leptogenesis. Therefore, this observation would point to this class of mechanism quite strongly. So I'll try to unpack these statements during the talk, all right? So here's the outline of my presentation. I will start with some basics of neutrino and some fun facts about neutrinos. I will then go into discussing massive neutrinos and the significance of double beta decay. And then in the second half, I'll talk about discovery potential of tone scale double beta decay, the current generation experiments, and in particular from the point of view of a theorist. I'm a theorist, so I'll tell you a little bit in the last part of the talk about my own research in this field. And I over-prepared, so probably I'll have to cut some apologies in advance. So neutrino basics. So neutrinos are elusive particles. In fact, they entered the scene in 1930 really literally as ghost particles. So Pauli postulated the neutrino, the existence of some light neutral particle to save the principle of energy conservation in beta decay. The beta decay was thought to be a two-body decay. There's an electron in the recoiling nucleus, but the electron had a distribution of energy, so there must be something else to carry it's not a line. So Pauli came up with this proposal. Fermi incorporated this in his theory of weak interactions, computed the spectrum, And by comparing, so this is Fermi drawing, by comparing with what was known back then as data, he concluded that the neutrino mass is 0, or in any case small in comparison with the electron mass. And just for reference, it took decades, 26 years before a direct detection of neutrino through the inverse beta decay. So antineutrino capturing on proton and giving out positrons and neutrons, and then almost half a century before establishing that neutrino actually do have a mass. All right. So, and we still don't know, as of now, we still, as I'll try to explain, there's many unknown in the neutrino world. So, neutrinos are elusive, but omnipresent, because they can be copiously produced whenever you have high density or high temperature environment. So in the early universe, they were copiously produced. They copiously produced in astrophysical sites like stars, supernovae, and so on. This makes neutrino second most abundant species in the universe after photons. They're omnipresent, but also it's very hard to study them because they have interaction very, very weakly, especially at low energy. Just for fun fact is right now, this is a picture of the neutrino, the sky, but in particular the sun in neutrinos. Right now, 10 to the 14 solar neutrinos are going unscathed through your body per second. Right? So the solar neutrino flux, and the energy of this solar neutrino typically of MeV. So if you take neutrinos energy of MeV, their mean free path in lead is 1/3 of a light year. 10 to the 17 centimeters. It's crazy, huh? So this makes progress in neutrino physics slow, but nonetheless, since 1930, we have learned a great deal of things about neutrinos. So I'm going to, without doing any justice to anyone who's involved in this, I'll give you a summary of what I think are the key developments, especially the things that we're going to use later in the talk. So, but first, foremost, in neutrino interact through gravity, but we now have established through the standard model that they form a weak isospin doublet with the charged lepton. There's 3 neutrinos, first of all, corresponding with the electron, the mu, and the tau. What does this mean? It means that the W boson, the gauge boson mediating weak interactions, can convert, let's say, into a positron and a neutrino of each flavor. So if you create a positron, you create an electron neutrino. If you create a mu plus, you create a mu neutrino, and so on. This context, the thing we've learned is that the smallness of low energy weak cross sections of neutrino is really related to the short range of the weak force, or in other words, the large mass of this force mediator. So if you play the number, just dimensional analysis tells you that the cross section have to go like the Fermi constant, which is 1 over squared, which is 1 over the W boson mass to the 4th times the center of mass energy. And so this gives you this 1/3 of a light year if you plug in the right energy. Second important breakthrough that we have learned is that neutrinos have a mass, have masses. So how have we learned about this? Through something called neutrino oscillation experiments. It turns out this is more of a theoretical concept. If you assume that neutrinos have mass, and the mass basis is not aligned, is misaligned with respect to the flavor basis. In other words, flavor state can be written as a non-trivial linear combination of linear superposition of mass eigenstates. Then a neutrino born in a given flavor propagate as a linear combination of mass eigenstate, and then be projected here and as a neutrino of another flavor, and produce here, let's say, a charged lepton of a different flavor, right? So you can do a simple model. This is the typical exercise that sometimes is given in quantum mechanics courses. 2 flavor mixing, right? There's a 2-state system, 2-state quantum mechanical system with a mixing angle and the mass splitting. These are the survival, P alpha. Alpha is the survival probability. P alpha beta is the probability of creating a neutrino of flavor beta. The oscillation length is related to the energy and the mass splitting of the neutrino, and the amplitude is related to the mixing angle, right? So this is a only thing that the undergraduate can do, and here's the real thing from experiment. It's astonishing, right? So this was done. There are many evidences of neutrino oscillation to many experiments, but here I think this is through reactor antineutrino in Japan, Kamlan. There's many reactors. There's a mine where they put a detector, and there's an effective flux average baseline length, about 180 kilometers. Here's the toy curve. The blue curve is the theoretical curve with the reflecting the real distribution of reactors, and the red is the data. So through this and many other experiments, we have learned a great deal about those mixing angles and the masses. But of course, if you remember this formula from neutrino interferometry experiments, you can only learn about the mass difference. So what do we know? We've learned that, here's the summary. The neutrino oscillation experiments can teach us that there are two mass splitting, both very small. If you convert this as 10 to the minus 3 eV squared, 10 to the minus 5 eV squared, cannot resolve yet whether the lightest neutrino is mostly mixed with the electron or not. This is the meaning of normal spectrum versus inverse spectrum. Look at the color. This would be the neutrino mass eigenstate mostly mixed with the electron flavor. Don't know if that's the lightest one. And we don't know the absolute scale because oscillating interferometry is only sensitive to mass differences. You can go back to the good old Fermi idea to determine the mass through the endpoint of some beta decay experiment to get this absolute mass. And there's an experiment called Catherine using tritium beta decay. They're looking very sensitively, but right now they're only able to put a limit. So they are about 800 milli-electron volts, so less than 1 eV, the absolute scale. This absolute scale, so which by the way is much larger than this splitting. So bottom line, what we learned is that neutrino have mass, but neutrino masses are tiny compared to the other fermion masses. So here's a cartoon by Hitoshi Murayama. Neutrino masses are below the eV. We don't know where exactly where this absolute scale is. The next heaviest particle is the electron, half an MeV, and then all the other fermions. So this is hopefully a snapshot of lightning introduction to neutrino physics and where we are. So you may ask, what's the big deal? Why? So this also is a big deal, right? This big gap is a big deal. Maybe it's telling us something about nature. But there's more. I'm entering the second part. The big deal is that neutrino mass is the same. Once you found neutrino mass, you found new physics beyond the standard model, because the standard model has basically built-in massless neutrino, in part because of the phenomenological success of the you don't see a need of a neutrino mass, in part because of the elegance of introducing only this left-handed neutrino that forms a doublet with the charged lepton. So no neutrino mass. We can, of course, can undo this. We can go back and write the neutrino mass. And of course, symmetry consideration provide a guidance on how to introduce neutrino mass. As you'll see, also how to discriminate the various options that we have to write down and introduce a neutrino mass. And that's what I want to discuss in the next few minutes. So let's start with symmetry, neutrino masses and symmetries. Lorentz, and I'm going to follow an argument given by Boris Kaiser. Lorentz invariance and CPT invariance give us two options, the so-called Dirac and Majorana. Let's get an intuitive sense of what a Dirac and Majorana neutrino means. Following Boris, we're going to consider a neutrino with momentum p. This is spin 1/2 particle. There are two helicity states, positive helicity, neutrino momentum and spin align, or anti-align. Let's start with a nu minus, negative helicity neutrino. CPT is a good symmetry. There must be another state, the CPT partner, which is a right-handed antineutrino. If you think what CPT and T do to nu minus, it flips the spin. And then if neutrino has an internal quantum number, it flips that. And therefore, we call it antineutrino, nu bar. For a massive neutrino, however, we know that helicity is not a good quantum number. I can do a boost, a Lorentz boost, and and the only thing that would change after doing the boost, I just change the momentum, the direction of the momentum with respect to the spin. You do a boost parallel to the momentum, neutrino momentum, and so you flip basically left-handed into right-handed. This state here will go here, and if again Lorentz is a good symmetry, this state must also exist along with its CPT partner, which you reach by a Lorentz boost. So these four states form a Dirac neutrino. So neutrino and antineutrino of both places. So there's two, there's an internal quantum number. What is the Majorana option? The Majorana option is essentially tells you that the state that you reach by CPT and the state that you reach by a Lorentz boost is the same. So you get the two states. That's two. So basically, what you call antineutrino here is just the other spin state of the neutrino. And you see, so this seems it's kind of clear. You can immediately see that this can only be realized in nature if a neutrino does not have any internal quantum number that is conserved, like a charge. Of course, with charge is fine. Neutrino is electrically neutral. This will work. But if you want to assign to the neutrino something called a leptonic charge, a lepton number, in the Majorana case, you're in trouble. You can't do it. You're going to run into violation of this. While in the Dirac case, it's fine. So basically, to sum up we have, in the Dirac case, four states. Two of them participate in the weak interaction, left-handed neutrino and right-handed antineutrino. These are the massless limiter, sterile, inert. If you write down field theory, the mass term, you notice that this can violate, if you add flavor, family indices, this violate flavor, but it conserves total lepton number. The Majorana case, we say neutrino is equal antineutrino because this new bar is simply the other state. If you write down, again, following the rule of Lorentz invariance, you notice that this is not psi dagger psi. It's psi psi. So if you make a U1 phase transformation, this is not invariant. This violates lepton number by 2 units. Okay. So very importantly, the two options are distinguished by this internal quantum number of lepton number. It's almost as an aside, I'd like to point out that both options require extending the standard model. The Dirac case, in almost trivial extension, you have to put this new R. New R, we don't have it, right? But you have to put it in. In the Majorana case, it's more subtle. This term that you try to write down is really at odds. It clashes with electroweak symmetry. So this cannot be. So remember, the neutrino is a part of a spin, or I just think of it, if you're familiar with spin in condensed matter, this is a spin doublet. And so this one, it has to involve a mass term, a covariant, an invariant mass term has to involve the electron field as well. This one doesn't. It turns out that you can write down a term that is SU2 invariant, a weak isospin invariant, but you have to go to higher dimensional operator. You have to introduce a new scale, and therefore this points to a new scale beyond the standard model. So it's a very, in my opinion, it's a very deep thing and often underappreciated. So this is my way of introducing why neutrinos are really taking us beyond the standard model. Now you may ask, but I mean, of course, I wouldn't be here speaking if you knew the answer. We don't know the answer. Which option is realized in nature? We unfortunately don't know yet the answer. In the next couple of minutes, I'll try to explain why. But the upshot, I'm going to anticipate the discussion. Smallness of the neutrino mass and the V minus A structure of the weak interaction, which implies some melicity suppression, mass over E suppression, really points to the fact that delta L equal to neutrino-less process. So if you want to learn about neutrino, you better look at processes without neutrino. Neutrino-less processes are our best bet to address this question of Majoranas versus Dirac. And you can take this as a statement, but I'll try to explain it in the next couple of slides. So bear with me. We need a little more detail about the way weak interaction work. So the W boson, as I said, can emit an electron and what we call an antineutrino. It has a V minus A chiral, so it's a chiral theory. In the massless limit, when the neutrino is massless, this thing only emits a right-handed antineutrino with an electron, and if you emit a positron, you emit a left-handed neutrino. Left-handed means spinning to the left, and helicity is a good quantum number for massless particle. When you turn on a mass, it turns out that you emit right-handed state, right helicity state with amplitude of order 1, but also an admixture, because like m over e, of a left-handed state. This is a Dirac case. This guy, both of them can, when they interact with matter, they can only give you a positron, right? The interaction of this, of the left-handed antineutrino is super separate. There's another m over e here in the vertex, right? So you pay a double price in the production, but both of them behave as an antimatter particle because they produce an E plus, an anti-electron. Let's look at what happens for Majorana. Again, the same story. You get an order 1 right helicity, or positive helicity state, and an order m over e, negative helicity. With jargon, particle and nuclear physics jargon, we say that the two helicity states mix through mass insertion, but we just say that this is emitted with the amplitude m over e. But now, this negative helicity state, when it hits matter, it can, without any additional m over e suppression, can give you an electron. This is what we call the neutrino, right? Basically, what happens is that depending on the helicity state, the neutrino, the Majorana neutrino, behaves as an antimatter particle. In other words, it makes positron, or it behaves as a matter particle. It makes an electron. So you're basically blurring, in some sense, the notion of matter and antimatter with neutrinos, with Majorana neutrinos. And so this is the key. So this is a key that, but there's a big but. The big but is that all of this effect is proportional to m over e. In order to detect this Majorana signature, which would be 2 electrons in a final state, or delta L equal 2, need to overcome this m over e factor. So for example, you can produce this neutrino in a pion decay, look downstream and check if it makes an electron or a positron. But the production amplitude is m over e. Those energies, and given that the mass is so small, makes it completely negligible. So there's 2 ways to overcome this m over e. One is to go to non-relativistic neutrinos, maybe the cosmic neutrino background. I'm not going to talk much more about that. The other is to have huge effective flux of neutrinos, which we cannot do with neutrino beams in laboratory. We have to somehow recycle Avogadro's number. We go inside the nucleus, and we make a big collection of nuclei. This gives you an effective flux, huge flux of this antineutrinos. So I'm going to explain more what this is. This is essentially neutrino-less double beta decay. So a couple of years after Majorana wrote his paper, Furry pointed out that if neutrinos are Majorana particles, inside the nucleus, virtual antineutrino can convert into a neutrino, mediate double beta decay, neutrino-less double beta decay. Because remember, if the Majorana neutrino, this is just a positive spinning, positive helicity neutrino, with the mass insertion that I told you about in the previous slide, converts into a negative helicity neutrino, and this can be absorbed with order 1 amplitude here. Okay, so this was Furry's proposal. So if neutrinos are Majorana, neutrino-less double, there's this new form of disintegration of nuclei at neutrino-less double beta decay. Key point in neutrino-less double beta decay is that lepton number changes by 2 units. And the exchange of light neutrino, like Majorana neutrino, is just one possible mechanism. Now we're going to abstract a little bit. And it seems funny, but Furry understood this. There are remarks in Furry's paper that say the Majorana theory is just one example, a canonical example of how this decay can happen, but it can happen more generally if you have violation of lepton number. So nowadays we have this other perspective. There could be heavier Majorana particles, like heavy neutrino, which I'll talk about in a moment, or heavy Majorana particles that appear in supersymmetric theories, and so on. The important thing is that you could have 2 down quark or 2 neutron converted into 2 protons or 2 up quarks and 2 electrons. Now, if you bear with me for a moment, if you observe double beta decay, all you know, strictly speaking, is something like this happens. And if something like this happens, through quantum fluctuations, loops in quantum field theory, or you can get back a Majorana mass term. You can write a diagram in which a right-handed neutrino gets converted into a left-handed neutrino through this high loop diagram here, involving only known particles, the W, the up and down quark. This observation was made by Schechter and Valle in 1982, and its importance is not quantitative, it's really qualitative. It tells you that once you observe double beta decay, there's no symmetry that protects a Majorana mass. You can write down a Majorana mass, so neutrinos are Majorana particles. Okay, so it's a two-way arrow. Neutrinos are Majorana fermion. Furry showed us the neutrino is a Majorana fermion, implies that double beta decay happens at some rate. Schechter and Valle showed us the opposite. If you observe double beta decay at some rate, neutrino, or by that matter, any process that violates lepton number by 2 units, you have that neutrino is a Majorana fermion. Okay? So that's quite important, I think. And so that's the main significance of why we want to search for double beta decay. There's an added bonus, right? The added bonus is the connection with baryogenesis. I tried to explain that Majorana neutrino really blurs the notion of matter and antimatter. And so Sakharov, in 1967, pointed out that a dynamical generation of matter-antimatter asymmetry during the universe evolution requires 3 elements. One, you need to violate you need processes that violate the conservation of baryon or lepton number. You need to create matter somehow, net matter number or baryon number. You need to do asymmetrically, so in other words, the CP conjugate process must happen at a different rate, because otherwise there are corresponding processes that make antimatter, and so you're back to square one. And you need to do it irreversibly, so in other words, you need to make sure that the inverse process, antimatter, matter annihilating, right, doesn't happen at the same rate. This is the departure from thermal equilibrium. So Sakharov pointed out, and there are many models realizing this. What's the role of neutrino-less double beta decay? Neutrino-less double beta decay addresses the first point quite directly. It's a delta L equal to process. Then there's a subtlety. Basically, the electroweak interaction in the standard model, again, blur the difference between lepton number and baryon number. Once you, through so-called anomalous processes, you can convert baryon number into lepton number and vice versa. It happens, it's a quantum effect at 0 temperature. It's a barrier penetration, so the probability is very tiny. Don't worry, the protons in your body will not disintegrate. But at high temperature, this is actually, in the early universe, this was a very fast process, almost in equilibrium with the expansion of the universe. So basically, if you show that lepton number is violated by 2 units, B minus L is violated by 2 units, you're gold with condition number 1. And then explicit models of Majorana neutrinos can satisfy the other 2. There are explicit scenarios where you can actually make this happen. And I'll mention one in a moment, in a couple of minutes. So these were the 2 big things. Nature double beta decay would really be the arbiter for Majorana nature of neutrino, and also establish the first of the Sakharov conditions. This slide, I'm going to skip it. Now, how do we search for neutrino-less double beta decay? How would experimental colleagues search for neutrino-less double beta decay? That's right, nuclei want to decay, as you know from text, alpha decay, beta decay, single beta decay, gamma decay. What's this double beta thing? It turns out that for certain nuclei, even nuclei, like these are some examples. If you look at the nuclear mass versus Z, the single beta decay is energetically forbidden. So look at this nucleus here. The next nucleus in Z, the charge, is heavier. So it cannot go there. It can only go there. So these nuclei are metastable. They were known for a long time. In fact, Maria Goppert-Mayer in 1935 was the first one to estimate the half-life of this. And she got it right, the order of 10 to the 20 years. And then, of course, it took until 1987 when this was first observed. So from 35 to 1987. Now, once you've observed the 2 neutrino mode, you want to now get greedy and look for the neutrino-less mode. And right now, there are several ton scale, meaning ton size of material, of active material, There are several of them, different isotopes, different technologies. Here's a few full pictures. The sensitivity right now in the current limits is half-life has to be greater than about 10 to the 26 years, depending on the isotope. The next generation will go by a factor of 100 in half-life. And the signature will be basically you look for the energy of the two electron at the endpoint, at the Q value of the reaction. The two neutrino case would have a sum of the two electron, would have a spectrum, but at the endpoint, it would be the neutrino-less signal. So the Q value of this nuclei, this reaction is a few MeV. There's a lot of radioactive lines in that thing. So typically these experiments are done underground. They use ultra pure materials. Sometimes even the cables generate noise, and so it's really super fascinating. But I'm a theorist, so I don't know much about this. The keys, the requirement from a theoretical perspective are energy resolution and background suppression. So otherwise, you're not going to be able to see these peaks. So I'm going to pause here. So this concludes the first part, the intro, the motivation. Hopefully now you'd like to know a little more about this. But are there questions so far on this? Yes.
This Dirac versus Majorana case. In both cases, have you checked that the gauge anomaly cancellation holds in the standard model?
Yeah.
What is the degrees of freedom in one case?
Yes, I think as long as you do you put the right number of families, yes, it does work. But, are there other questions?
Conservation of barrier number minus lepton
Yes.
number,
Yes.
as you said, is a symmetry in the standard model, but that also hinges upon the existence or non-existence of right-handed neutrinos.
No. B minus L comes from the electroweak anomaly, right? So B plus L is violated and B minus L is preserved. It assumes, to compute that, you need to assign weak doublets. So you assume that the left hand, the neutrino, is part of a weak doublet, so it's part of this loop. Yeah. The right-handed, I'm not making any assumption. There may be a right hand, but it's singlet under that's the assumption. Right?
So that just carries forward even if you assign a Majorana mass to the neutrino.
Yes. The questions?
So I come from a condensed matter background where we often study unpaired Majorana zero modes, which are sort of like low energy condensed matter counterparts of the Majorana fermions as neutrinos. And I just want to ask you kind of an awful question. Are you aware of any like condensed matter attempts to try to understand the origin of mass, possibly for Majorana-like particles?
It's a great question. I'm not aware. I'm really not an expert. I'd like to learn more about this. Actually, yeah. I hope after the colloquium, I know there's a condensed matter crowd, and some of you have worked or are working on Majorana modes. So unfortunately, no. I don't have any insightful comments.
I'm trying to translate everything into like a condensed matter counterpart. But to my knowledge, there isn't this like effort in the condensed matter community to try to like understand the mass, possibly, of these particles. This is like a purely high energy, like particle physics effort, to my knowledge.
Yes, to mine too. And then yeah, unfortunately, yes, it's a little disconnected, but yeah, maybe. Yes.
I think I might miss something somewhere. So I wonder what is the sharp signature for the non-vanishing of the lattice neutrino?
What
is the sharp signature for the non-vanishing of the lattice?
The oscillation. Those neutrino oscillations can only happen if you have a mass splitting. To have a mass splitting, at least one mass has to be non-zero, right? So you asked for what is the evidence
for the non-vanishing of the
non-vanishing of one of
the lattice.
Oh, the lightest one. Sorry. Yeah, it would be. You would show up as an endpoint here. So in the endpoint of beta decay, you would see a there's a dependence. So the beta decay emits all three of them, right? All three neutrino, 1, 2, and 3. And you do an incoherent sum. This is what it's called M beta. Depending on where this endpoint spectrum ends, you can reconstruct the light. But you can reconstruct this quantity, and if you know the mass splitting, you can reconstruct the lowest one. You know the mass splitting of the three. If you know this linear combination, you can reconstruct which is the lightest.
Is there a sharp signature for its non-vanishing? Is there a sharp signature for its non-vanishing? I mean, I don't know. It's still like, if you do this calculation, you got something which is extremely small. I'm not sure whether that's an error or not. Something like this. So I just wonder if there's a proper signature. Like, for example, for photon, I know like there's a sharp signature for whether the mass is zero or not.
That's a good question. Yeah, I'm not aware. I think this is a continue. Yeah, you say, oh, it depends, of course, on the energy resolution and so on. Yes, I'm not aware. Maybe people in the audience, maybe were sharp, if there is a sharp signature. Yeah, a good question. Yeah. Okay, so maybe I continue. All right. So all the arguments so far were really qualitative, but there's also an exciting quantitative aspect to this search for neutrinos double beta decay. And so we want to ask the question, so are all these big experiments a shot in the dark, or is there a some target or some quantitative goal? And I'll try to argue that these searches at this level of half-life can actually discover lepton number violation arising from a broad variety of mechanisms. And in some cases, we have quantitative goalposts. In others, less quantitative, but still plenty of discovery potential. So to illustrate this, this is my picture, my cartoon of theory space from a phenomenologist's point of view. One axis is increasing mass scale of the physics. One axis is decreasing coupling strength. Somehow we live here. We've explored. The standard model lives in this corner where the mass is smaller than 100 GeV, and the couplings are sizable, not tiny. As you move along this axis, you go into the so-called dark sector. As you move along this axis, you go up to the grand unified theory and so on. But technically, the new physics could be anywhere, unless you have a... and my perspective is somewhere out here must be physics that explain neutrino mass, right? And if the neutrino mass is Majorana type, double beta decay is the best probe for most of the parameter space. Other probes, as I'll show towards the very end of the talk, can compete in limited region of this parameter space. Like colliders can probe maybe around here, just above a few hundred GeV and so on. So I'll try to convince you that, so now I'll give you an overview of some popular models. Let me start with perhaps the most popular model, the high-scale seesaw, which would live up here, right, in this plot. And we have here Pierre Ramon, who was one of the inventors and proponent of the. I'm not going to again do justice to this. I just want to say that in this class of models, the simplest way to represent this class of models is to think that there is a right-handed Majorana neutrino, a singlet. Now you can write, and it's very heavy. You can write a mass term for this consistently with the symmetries of the standard model. Of course, this UR is most likely embedded in some grand unified representation and so on. So, but if you think from the low energy perspective, this is a singlet. You can write a mass term. This mass term now, when it talks to the Higgs and the lepton doublet, it generates a mass term for a Majorana mass term for the light neutrino. So this becomes very heavy. It shrinks to a point. Doesn't propagate. You get something like this. And if you plug in, so if you look at the structure of this mass for the neutrino, it's going to be proportional to this y square, which we take 1. Remember, we're here, large coupling. Electroweak expectation value of the Higgs, which is 100 GeV squared, divided by the mass of the right-handed neutrino. Turns out if you plug in, if you want to have electron volt or less scale, MR has to be very heavy, 10 to the 15 GeV, very close to the grand unification scale, and this is standard picture of the seesaw. So in this way of generating neutrino mass, light neutrino mass, this is very attractive because it also explains why neutrinos are so light and so on. So it's an extremely popular class of models. In this class of models, the only low energy remnant of lepton number violation is the light neutrino mass. For Farri's mechanism controls double beta decay. But there's an extra bonus. This class of models, as I promised, would show you a little bit of glimpse of baryogenesis. So in this class of models, this heavy right-handed neutrino, they're not just there to give mass to the neutrino, they do something else by decaying in a CP violating way and out of equilibrium way. So it's lower than the expansion of the universe. If they decay out of equilibrium, they can generate a lepton number, lepton asymmetry, and then this lepton asymmetry is converted by this Farreron process into a baryon asymmetry. The celebrated leptogenesis mechanism by Fukujita and Yanagida. This lives up here. Okay, doesn't have to be like that. There could be models at intermediate or lower scale, like the left trisymmetric models by Mohapatra and Senjanovic. And these have more mechanisms to generate double beta decay. There is for example, there is a way to do double beta decay, which is a completely right-handed version of the picture that you showed that I showed earlier. Right-handed W, much heavier than our usual W. Right-handed neutrino, much heavier than light neutrino. When you look at it at low energy, this is a point-like operator suppressed by 5 powers of the heavy scale. There's 1 neutrino mass downstairs and 4 powers of the heavy mass. And there's many, many others. This is just an example. I just want to convey how rich this is. This contribution can compete with and give a signal if the scale is not too heavy, maybe 10 to 100 TeV. And of course, it's even more rich than that because at the low energy, at the nuclear level, hadronic and nuclear level, give rise to other mechanisms. They could be, actually the dominant case in some cases, in most cases, is a pion, 2 pion double beta decay. You make pi minus going to minus and minus, and then you embed that into a nucleus. So there's a whole richness of physics coming from when you go try to put these things inside the nucleus, which we use for experiment. And last but not least, there could be light sterile neutrinos that are, again, our gateway to the dark sector, and they could also contribute to double beta decay. So hopefully this survey gives you a sense that from the theory of neutrinos double beta decay is as hard as the experimental. They have a lot to work to suppress backgrounds, but the theory, if you want to make quantitative prediction, is extremely hard. And connecting lepton number violating physics, it could be on any scale, to nuclei is a multi-scale problem, which is best tackled through this concept in physics called effective field theory methods. That, by the way, I'll argue that it's the only chance that we have to achieve control uncertainties in this nuclear calculation. And this is where I started working on this a few years ago. We developed a coherent framework. Bits and pieces of this framework, effective field theory framework, existed, but we developed with collaborators here a more coherent and framework, which also led to some surprises. So the idea is that new physics could be anywhere in that plane, remember? But if it's heavy, you can integrate out the heavy particles. You can map that plane into a series of a string of local operators, right? Because if they're heavy, quantum uncertainty principle tells us that at low energy, delta E, delta T, or delta X, delta P tells us they show up as local interaction. And it turns out that for delta L equal to interaction, you can only write operators involving low energy particles, dimension 5, 7, 9, so 1 over lambda, lambda cube, lambda 9, and so on, lambda 5, and so on. If you want to include right-handed neutrino, this can be done. And its counting is slightly different, but for now, let me stick to the no right-handed neutrino, no light right-handed neutrino. Then you evolve this interaction with the renormalization group down to the hadronic scale, the non-perturbative scale, where strong interaction, quantum chromodynamics become non-perturbative. And it turns out you have to switch degrees of freedom. You have to talk about pions and nucleons, and then generate ion and nucleon transition operators that then they go into the nuclear wave function and give you the transition amplitude, the S matrix element. So basically, as this schematic formula gives you, the effective theory, the power of effective theory is that you organize your half-life calculation in terms of ratio of scales, of widely separated scale. Let's say the weak scale divided by the scale of new physics. Scale of QCD 1 GeV divided by the weak scale to some other power. Then the scale of nuclei under MeV, K Fermi, the Fermi momentum inside the nucleus, of nucleon inside the nucleus, divided by the QCD scale, 1 GeV, to some other power. So this, somehow this now seems obvious, but somehow in the literature, this step of going from quarks to the hadronization step was usually missed or mistreated. People were aware of these currents. There are weak currents or weak operators, and then they skip directly and they put them in a nucleus as nucleon currents. But by doing so, you're missing a lot of QCD physics, and I'll try to illustrate in a few cartoons what that means. And this is very important if you want to achieve quantitative understanding and try to tell your experimental colleagues, what are you probing? So I will start with this dimension 5 operator. This is again the effective theory version of the seesaw, essentially. If lepton number evaluation originates at very high scale, the dominant low energy operator is the leading of power. The first one you encounter is this dimension 5 operator. Weinberg showed us that there's only one operator you can write down. If you are technically oriented particle physicist, you should understand what it is, otherwise just ignore it. It's just take it. This is a Majorana-Mas term for the light neutrinos. And once, at the same time that you do this, you have to take into account all the beautiful quantum chromodynamics. So this thing happens as it evolves down in scale. It also evolves with the QCD. So the diagram, the simple neutrino exchange, 3-level neutrino exchange, get dressed up by gluons, and then QCD becomes non-perturbative. This picture becomes, you would have to include more and more gluons, and that's when we switch to the hadronic picture. I'll go back to the atrocities of this hadronic calculation, but I want to make a comment. Regardless of the complicated QCD and nuclear dynamics, there's only one delta L equal to parameter. The theory, this m beta is the neutrino mass in the flavor basis component EE. The double beta decay has to be proportional to this, right? This makes double beta decay special because, unlike other searches of physics beyond the standard model, we've already discovered this operator, right? Neutrino oscillation also probe other aspects, the lepton number conserving aspects of this operator. So basically, the point I want to make is that we already discovered this effect, other effects of this dimension 5 operator through neutrino oscillation. And therefore, the half-life, in this case, is related to all these neutrino mass and mixing parameters. And this gives us very clear discovery targets. This is the one example where we know what to look for. It's very unique in particle physics and nuclear physics. In all the other cases, you don't know where the scale lambda, you just put bounds. Here we know, sort of. Okay? What do you mean that we know sort of? Again, up to the fact that we don't know the absolute scale of neutrino mass and the ordering. So, in other words, formulate that up to the nuclear matrix element, the decay rate is proportional to m beta beta. This depends on the mixing angle in this U matrix and the absolute and the neutrino masses. So we usually we don't know exactly what this is. We parameterize in terms of our ignorance. We have two branches, one for inverted ordering of the spectrum, one of the normal ordering. We don't know the lightest neutrino, so we parameterize as a function of the lightest neutrino mass. Then we parameterize, we marginalize with respect to some phases, so-called Majorana phases that are in this matrix U and are unknown. So that's why these are not lines but bands. Okay. This is what we know about m beta beta. So if you have a range of matrix elements and you have a range of bounds on the half-life, you can ask, where are we on this plane? How far from discovery are we? We are here. So this is the Kamland-Zen experiment for a range of matrix element. Is almost touching this, starting to cover this region. Of course, this branch we're already excluding. You could have seen it. If the absolute scale of neutrino mass were higher than EV, you could have already observed neutrinos double beta decay, right? So this is where we are, and the goal of the Thorne scale is somehow to cover this entire inverted ordering region, but also there will be discovery potential on this other branch as well. So you need inverted spectrum or M lightest greater than 50 millielectron volt, and you can still see in normal ordering, you can still see double beta decay. All right, so this is the concrete target for this generation of experiment. And I would argue that since neutrinos are really the only concrete laboratory-based evidence of ESM, one should gear up also for the next gap. Another factor of 100 could probe this normal ordering, and there are ideas experimentally on how to do this. It's very challenging, but the next goalpost is millielectron volt for M beta beta. I'm going to skip the next slide because it's in the same spirit. I want to say there are falsifiable correlation with cosmology and other direct mass measurement. I want to talk a little bit about my own work, but my own work is motivated by the fact that we need, in order to make this quantitative connection, we need to know more about those matrix elements. This band here corresponds to an uncertainty of factor of 3 or 4. The matrix elements in some units 2 plus or minus 2 plus or minus 1, or right. So how do we do that? As I said, we do this EFT treatment. And a key new insight from the EFT, which I was involved with his collaborators, was that, again, this gluon exchange at low energy at the nuclear scale looks like a short-range interaction, still proportional to M beta beta. There's the usual Coulomb-like potential mediated by neutrino, but there's also this short-range interaction, which comes at the same order in this power counting in Q over lambda chi, let's say the nuclear scale over the QCD scale, and 100 over MEV over GeV. The reason for this, it comes from the interplay again of the strong and weak interaction. It comes from really renormalization group amplitude. The leading order scaling is required when you try to compute the amplitude, let's say, of the simplest double beta decay, the 2 neutron to 2 proton double beta decay. This effective theory, you have to include this short range nuclear neutron proton interaction. These are needed to explain the large scattering length of the nucleon system. And once you do that, this diagram is divergence, generate the RGE that brings this guy, whatever you start at the high scale, it flows to a large value at the nuclear scale. Okay, so that was the new insight, and then of course, this is the kind of dramatic. We don't know its value, right? In EFT, you encounter effective couplings all the times, but then you usually fit them to experiment. Here we don't have an experiment. We need to come up with a prediction of this effective coupling, and we tried. First, we wanted to use symmetry arguments to get it from experiment. That would have been fantastic, but unfortunately it doesn't quite work. But the symmetry argument is beautiful, so I want to spend 1 minute discussing. It has to do with this weak current. So basically, the upshot is that a massless neutrino running through this loop and a massless photon running through this loop, the isospin symmetry for the nuclear system is the same. Because this current, the weak current that is inserted here, and the isospin 1 component of the electromagnetic current, just a isospin rotation of one of the other. Fortunately, again, this chiral structure of the currents bites us. Weak current is only left-handed, electromagnetic is right-handed, so there are 2 couplings here and 1 here in the neutrino in the weak sector. So we could get only 1 combination from data, the sum of these 2, the vector-like combination, which corresponds to the photon. Nonetheless, you can assume there are also large NC arguments that back this up. The G nu goes like the sum. The vector is, and the left, they're all the same. The left and right are similar. Then some nuclear structure colleagues did the analysis, and it's really a dramatic effect. It's an order 1 effect. If you include it, adding with a plus sign, you're much closer to probing, discovering physics. If you include it with negative sign, you're dead. It's another order of magnitude to go for the before you can get to the interesting region. And so that somehow propagated through the community. The largest QCD community is gearing up. There's several collaboration gearing up towards computing this. And with another set of collaborators, we came up with a dispersive method. Basically means open up this thing and look at this Compton amplitude. Basically a W plus to neutron going to W minus to proton. If you know this for all values of the photon, of this W momentum, you're done. You can determine this low energy constant. And spare you the details, we use the arsenal of theoretical tools to come up. It's still model dependent because it's the intermediate momentum region here is a bare, is fully non-perturbative. But the result is that when we feed this into we talk to the nuclear structure colleagues, and they insert it in their nuclear calculation. It's a positive interference. So it enhances the matrix element by about 50% for the isotope of experimental relevance. So it's very good news for phenomenology, but big caveat, the ultimate word here will come from lattice QCD in the next, I would predict the next decade or so, the next 5 to 10 years. Okay, so let's see, how am I doing the time? We have 5 minutes, okay, great. This is, you can ask me later, then this is not the final step. You have to put this again into ab initio, first principle nuclear structure calculation. There's a significant number of groups in the US working on this. And now they can try to quantify the error. It's all based on this low energy effective theory of QCD. And uncertainties are still 50%. But you can see here, using our input on the operator, this is only become a minor error. The larger error is the many-body truncation. Different many-body methods for solving the nuclear many-body problem give different values of the matrix element. But there's, it's improvable. A few words on this other mechanism. So this is the dimension 5, the high scale CSO is interesting because we have a precise target, but it's not the only. Stevie scale mechanisms are interesting because they arise in other models of neutrino mass, like left-right symmetric model. They can lead to correlated signals at colliders, like 2 protons going to 2 same sign lepton and 2 jets at the Large Hadron Collider. There's many operators, so the inverse problem is difficult. And one other comment I want to make is that, again, the low energy nuclear physics is also important. You can fool yourself and miss orders of magnitude in the bounds if you don't do the proper chiral counting. Just a couple of examples on the phenomenology. These are now these contributions are not correlated to light neutrino mass. And they can add incoherently with the M beta beta or interfere. This is an example of some version of the left-right symmetric model. You have an incoherent contribution, so it's optimistic. So that you would have much larger effective mass if you had this short-range contribution. So much closer to the experimental bounds. And then this is the pessimistic thing, but you can also there are scenarios like leptoquark scenario where you can interfere. What was considered favorable, the inverted ordering, you don't know. You can interfere dramatically, and the rate could be anywhere depending on how the M beta beta and this new operator contribution interfere, depending on the phase. It could be anywhere. While in the inverted ordering, you can be up here. You can be enhanced where you thought you were oppressed by just the M beta beta. So these are all just to say that we need to be open-minded when you think about double beta decay and neutrino masses. I'll skip this one. You can probe masses in the from multi-TeV to hundreds of TeV. They're beyond colliders. So there's a, yeah, this is maybe an important point. We've done a comprehensive study. We can't point to size target, but we can definitely say that none of these parameter space is being probed by anything else, by collider. So, and the neutrino mass mechanisms could be at these intermediate scales, and if it's there, double beta decay can definitely probe it. Last minute is the connection to collider physics and the EIC. When I say correlated or precursor signal at the collider, I mean that take this amplitude and you do crossing. Well, actually for LHC you don't even need crossing. You pick down quark, 2 down quarks from the 2 protons, swap quark give you 2 jets, and then 2 same sign lepton. This is signature at LHC. DIC you have to do some crossing. You take 1 electron on one side and the other on the other. Then you also move around the quark legs. You have EP going to E minus P going to positively charge 3 quarks, which I learned is not the same as 3 jets. But so this is quite interesting. In whenever the collider has kinematic coverage, you can probe this same physics also at the collider. It turns out that the largest sensitivity is whenever you have resonant enhancement. So when these particles are not too heavy, right? So you open up this blob, and this is a classic example, left-right symmetric model. But so there's a lot of activity now to see what the EIC can do here. I'll skip this slide and I'll go to the conclusion. So hope I conveyed the message that observational double beta decay would address big questions. I think there's significant discovery potential because we don't know the mechanism. So, and even if we know the mechanism, there's even there in the high scale, there is significant discovery potential. EFT approach can be very useful on 2 fronts. It relates double beta decay to the underlying sources of lepton number violation, models of lepton number violation. It can be very helpful in organizing the contribution to the matrix elements. In fact, interesting things have happened here already. Very optimistic because of experiments under construction and also the possibility of probing lepton number and Majorana nature of neutrinos colliders. Thank you for your attention.
Thank you so much, Vincenzo, for this very pedagogical colloquium and this informative presentation. Questions for Vincenzo? Yes, Peter.
So what is the status of the next experiment?
So, excellent question. So there are there are 3. So R&D in the last 10 years developed 3 big experiments that are ready in principle to construct at the ton scale. Legend with the germanium, Nexo with xenon, and Cupid, which uses molybdenum 100. So Legend, as far as I know, so these are expensive operations. So each of them is in the hundreds of millions of dollars or euros. It's invariant at that point. And so you need international cooperation. As far as I know, Legend 1000 is a green light from the US and Germany and Italy. So it's probably the most likely to happen. Cupid is a little cheaper, and it's probably going to happen without huge US participation. Just Italy and maybe Germany. And Nexo is mostly a Canada-US enterprise. So far, there's no commitment from the US. So that's as far as I know. So probably 2 will happen. They're both at Gran Sasso lab in Italy.
More questions?
Okay. So slide on the challenges,
Yes.
you had made an estimate of the half-life,
Yes.
but you left the exponents unspecified. So is there a way to estimate the half-life, probably using just tree-level physics?
Yeah, actually, yes, that's a great question. It was very schematic. Typically, the first couple of exponents are easy. You can do it perturbatively. Yeah, actually, let me go back to this slide. Yeah. Step is perturbative, typically. This step is perturbative, running down. Non-perturbative steps are hadronic matrix element and nuclear matrix element. So this first two powers are known for each mechanism. For each of these operators is basically known. So let's do for the the high scale seesaw. Well, it's easier for me to think about the amplitude. The amplitude is going to be 1 over lambda squared. Amplitude is 1 over lambda, right? So the rate is 1 over lambda squared. Then this q over lambda chi is actually starts is 1 over q squared. This is a negative power, right? At the amplitude level, because this is a neutrino exchange. It's like a Coulomb potential, where q is the tip. So that, of course, taken into the nuclear wave function, it scales like whatever it has to scale, the power of the radius. So you can, but that's the leading term. Then the chiral EFT tells you that after the 1 over q squared, there's going to be 1 over q and 1 over q to the 0, and then positive powers, okay? Right now, we know amplitude up to 2 powers. So 1 over q squared, 1 over q, and 1 over q to the 0. In most other mechanisms, we only know the leading power. So, but because of the relevance of this dimension 5 operators, is impetus to go beyond leading power. But in most cases, we know at least the leading power in all of these. Thank you.
These MBT beta plots with the normal hierarchy,
Yes.
is this feature of MBT going to
Yes.
is there some simple explanation?
Yes, great question. The simple explanation is because this matrix U contains this is not, see, it's UEI squared. There are some phases, basically the interference of some unknown phases, Majorana phases, and when you marginalize over them, there will be lines that go like that. They have an exact 0 at some point. Then when you marginalize, it becomes a funnel. So it comes from this known Majorana phases. And we say, oh, you're going to be in the funnel. This plot is very misleading because you could be, I mean, I could plot it 10 to minus 5, 10 to minus 10 EV. It's equally, I mean, a priori. So it would look like that's the way which somehow the community chose to do this, overemphasize this funnel. Right? So it is there. There is a chance that you live there, but there's no symmetry that tells you that you're going to be there. So I would not be too overly worried.
To some 1 part in 100 or something.
Yes.
It cuts off.
Yes.
Moderate,
Sorry, can you
assume these aren't fine-tuned for like 1 part in 100 or something like this?
Yes. In fact, there are some studies with Bayesian. I don't have a backup where they actually randomly throw according to some prior phases, and you never really fall into the funnel. No, that's great question.
More questions for Vincenzo? Okay, I don't see any, so let's thank Vincenzo again.